So I think my talk is going to be quite different from most of others here, because I think I'm maybe the only one, or I don't remember, that I'm showing some experimental work, but with some theory that supports this experiment. So as Andrew said, so I'm currently here in Singapore since October at SUTD. But this particular work, I developed this while I was still in Brazil for my PhD that ended in September. And this talk is going to be based on a paper that came out on PRL November, so quite recent. It also received a viewpoint in physics about paper. So it's an experimental realization of the rectification of entropy production. So in the in thermodynamics way, so non-equilibrium process creates some entropy, but by by measuring and acting based on the result of the measurement, so exploring information, this entropy production can be rectified or minimized, and we're going to see how to do that. So the viewpoint says that the theory of the Maxwell's demon meets non-equilibrium thermodynamics, and so as I said, so this as the people that are involved in the work, so we're here in São Paulo that would develop most of the theory. Actual experiment was done in collaboration with people in Rio de Janeiro at the CBPF, and now I have moved to here, halfway across the world. So there's this, we have two basic theories that we are putting them together. So one is the non-equilibrium thermodynamics, which is characterized, I think the main object of non-equilibrium thermodynamics are the fluctuation theorems, which are, in a sense, generalizations of, for example, second law. So Chiara mentioned just recently now a breakdown of the second law at some scale. And I'm going to show here not a breakdown, but a refinement of the second law that is valid at lower scales. And the information theory, which is as a fully fledged theory, is quite recent, so 1948 with Shannon, but the spirit of information theory was already present in the works of in the Maxwell demon or the Szilard engine much earlier than that. So the Maxwell demon is the construction about Maxwell's that to operate a small gate, so in a gas that is at thermal equilibrium. So the second law says that you basically cannot do anything with that. You cannot extract work. But if you operate on a molecular level and open the gate, so measure a molecule's velocity, and then you make a decision based on this measurement to open this gate for a fast molecule or close it for a slow molecule, you can make one side of this chamber to be hotter than the other side, and now you can do something with it. You can extract work from. The Szilard engine was a construction that's very also similar on that. You measure which side the particle is, and you make a decision based on that, and then you make a thermodynamical cycle that extracts work from a single temperature reservoir in a way. But then, which is something that second law seems to forbid. One actual point that was missing from their discussions on Szilard was that this last step, which is erase the memory from where the particle was, to be able to actually close the cycle and start it over, was considered to be kind of a trivial process. They didn't really pay attention to that. But then Landauer, so 1962, said that no, this is actually an important step. It's not a trivial one. It cannot be done with a unitary reversible system. It needs to include some irreversibility, and then it needs to include some work that has to be performed, spent, and the work that must be performed here is at least equal to the work that was extracted from the machine. So the machine is energy neutral or energy loss when you include the memory cost of erasure. And now here is the part that I mentioned about the refinements of the second law. So one way of writing the second law is that there's a system in thermal equilibrium. This system is subject to some external constraints. So let's say the volume of a gas, that's the piston where the gas is constrained. And these external constraints are changed. So the volume is changed, for example. And this process needs work to be done, or they may give you some work. But they also involve a change in the free energy of the system. And the second law is an expression that the work that you need to spend to make the transformation is at least equal to the free energy that the change in free energy. And you can interpret the free energy as something like an energy that is easily available that you can extract work from it in the future. So the present cost is always larger than the future availability of work. In quantum, or in not necessarily quantum, but in small systems, this is true on average. But there's this another equation which is more general, which implies this one in a logical way, where the average of this quantity, so beta here is the inverse temperature of a system that has started in thermal equilibrium with that temperature, equals to the exponential of free energy. So even though this is an inequality, this is an equality that is valid for arbitrary process, even ones that are far away from equilibrium. And this is actually, so this was known since 1997 in a classical way, and it applies to quantum systems too. But this is also a particular case of a more general relationship that it's a relation between the probability of a process happening on a forward direction and some quantity of work being spent on that process, and the comparison of the same process happening on a backwards direction. So it could be the expansion of a piston and the compression of the same piston with the same speed in absolute sense, but signs reversed the speed. So we are going to use something that looks like this, but including now some information about the system. So the general setup of a daemon here, so we start from a thermal equilibrium state. There's a unitary driving, so there's a change of some parameter. So let's say, in this case, that's going to be the magnetic field that a spin is subject. And so this laws, the Jarzynski relation, the second law that I mentioned, they would basically stop here. But what we're continuing, so we have a paper 2 years ago that basically stops here. But now we included that the daemon makes a projective measurement on the system, and then depending on the result of the measurement, there's another operation that is performed on the system at some later time. This we consider to be an unitary evolution. This we consider to be a unital operation, which is something that's more general than a unitary. So a unital operation is one that keeps the maximally mixed state a maximally mixed state. So it includes every unitary, but also includes some dephasing maps, for example. It's a more general condition. And the Jarzynski equality that I said that e to the minus beta w becomes, we must consider this term here, which is a mutual information between the daemon, the memory that has recorded the result of that measurement, and the state of the system. So we have this the unaveraged term of the mutual information, and from this is exact result, and this leads to using something that's called the Jensen inequality from mathematics, from value for convex functions, leads to this equation that, so here's the entropy that is produced because the system is, your evolution has happened away from equilibrium. So it's beta w, sorry, there's a mistake here. It's beta times the work, so the work span minus the free energy variation is not larger than 0, but it's larger than minus the mutual information that you have obtained from the system obtained. So the mutual information can be converted into work. But while this equation, so it doesn't rule out this possibility, it also doesn't tell you how this can be, it's not a constructive equation. So we move to a constructive equation by considering an exact expression that is composed. So here it's a equality, it's not an inequality, that involves these three terms. So there's this quantity called the information gain of a measurement. So it's the average reduction of von Neumann entropy that you get from a measurement. So it is the von Neumann entropy before the measurement minus the average von Neumann entropy after measurement. This is always a positive quantity. And because of this minus sign means that this quantity might make the average entropy production to be negative in this case. It's important to note we're not considering the cost of erasing the memory later. So, and then these two terms are a divergence, so some way a distance, not exactly one, between the state that we actually get at the end of the protocol and the state that we would get if we had a thermal reservoir at the end of the protocol. So, and here is the average change in von Neumann entropy, so due to our feedback protocol. And so we need to design a measurement scheme that would satisfy this to actually obtain what we call it efficient daemon. So a daemon that actually converts information into energy and gets a useful. So I will talk a little bit more about these two terms here. So I'll go back to this thing. So we start from, even though we start from a thermal equilibrium state, there is no more thermal reservoir. The interaction between the system in the lab, all these steps are done in a time that is very fast compared to the interaction with the system, with the reservoir. So the system is basically uncoupled with the reservoir after the initial thermalization. And then so and then so it follows here a map that is and gets to a state. So some parameters of the system are changed here. So it's a time-dependent Hamiltonian here. Here we also have, there's another time-dependent Hamiltonian, but that Hamiltonian that depends not only on time, but also depends on the results of this previous measurement. And we also include some mismatch or some probability of a classical error on this information processing. So we measure the L, but we actually record this as having measured K. And then, so that first term, which is the Kuba equilibrium difference, so it means how close this state is to the thermal state that we would have obtained if we let this state thermalize with the reservoir. So it's how much the state changes with a thermal reservoir. And the other term is a increase in von Neumann entropy. So the experiment was done with a NMR system, so nuclear magnetic resonance. It's a chloroform molecule with carbon 13. So it's essentially a pair of spin 1/2 systems, so a pair of two-level systems, where and then the carbon atom, the nuclear spin of the carbon atoms, we're considered as the thermodynamical system of interest, while the hydrogen atom we'll consider as the daemon, the quantum memory. And why NMR? So we have this. One advantage of an NMR is because of this term, the Hamiltonian, two-body interactions are easily or are very feasible and can be done very good precision. There's very good experimental control of the operation, so the fidelity of operations are very good. The relaxation times are quite long, so the order of seconds, while the time of applying operations are the order of milliseconds. So lots of operations can be applied while the system is basically uncoupled from the outside world. The only issue is with scalability, but for small scale, few qubit quantum simulations, it's maybe one of the best that offers the best possible experimental control. So we do the process where we have a unitary change of a Hamiltonian. So we start with so the Hamiltonian here is just an external magnetic field that we apply to the spin, and then we change this the intensity and the phase of this magnetic field. So, and then this is a measurement. So there's a C0 gate and a gradient. So to that, and then we include this rotation here, which is essentially a classical error on our readout of the measurement. So even though we measured some value, we might like record it as having measured a different value. And then based on the result of that measurement, if this turns out to be a 0, we apply this operation. If this turns out to be a 1, we apply another operation. So this is and this is a important part, this back action on. So we changed two parameters here. We changed. First was the effective temperature of the initial thermal equilibrium, and second, thus the amount of error on the processing of this information. And we got negative average entropy production as we wanted. And here, for example, some trade-off relations that are important is that so those two terms that I said, they cannot be maximized or optimized together. So, for example, by increasing the temperature, so we go to states that are more like high temperatures, so they're more random in a sense, the information gain decreases. So this makes that, so this limits the efficiency of our Maxwell demon, because at high temperature, the information gain is small because there's not much information to gain. The system is a very random state. So the entropy production goes to 0 at very high temperature. Now, we keep a fixed temperature, but we change this control-based mismatch. So the information gain is fixed because this mismatch is related to, so because the information gain is what the information, that the measurement gives, but this is not enough to get a negative entropy production. You need to act based on that measurement, and if you have a big mismatch here, then it means that this back action is not being effective. So the mutual information is actually being degraded here, not the information gain. So we see also that, for example, when changing the temperature, this term here is constant, but we are optimizing over this term, but at changing the mismatch, we are optimizing this term, but this one is actually decreasing. So these two terms cannot be optimized together. So it means that a very efficient Maxwell demon, one that saturates that the Jarzynski relation, one that extracts a quantity of work that is equal to the mutual information, is not possible in general. So because these two terms here have generally opposite behaviors. So that was what we did. So we showed that information can be converted into energy, or free energy more specifically. But this process obeys some fine-grained fluctuation relations that are some generalizations of the thermodynamical relations, and that to do that in reality, in experiment, we need to be very smart about how to do the feedback process, and the feedback process is in general not perfect in the sense that like to achieve the equality on the second law, but it's possible to get useful information to energy conversion. And understanding these concepts, it's very important for like small scale thermal machines, which is a field that is growing rapidly in popularity. Very different experimental implementations are happening in the last very few years, and it's a field that is growing very consistently. So thank you very much.